we have radical 1 minus y squared dx minus radical 1 minus x squared dy equals 0. And this will be an initial value problem. So for our initial value, we will have x at 0 equal to radical 3 over 2. Now remember, the goal here is to separate the x and y's. That's why they're separable variables. So you want x on one side and y on the other side. So first step in achieving that is adding the 1 minus x squared under the radical over, and then dividing the radical 1 minus x squared and the radical 1 minus y squared. Next, we integrate. Now this, if you look at both of the integrals, they're both structure-wise, they're identical. And they're in the following form. The integral of dt over radical 1 minus c squared. So if we can solve for one, we essentially solve for the other. But how do we go about solving this? Now, if you probably refer back to calculus 2, you can see that this will involve some sort of trig identity. And how will it do that, you say so? Because look at the term 1 minus t squared. It looks a lot like the certain trig identity that we're familiar with. This trig identity, where sine squared theta plus cosine squared theta equals 1. This essentially is an equation of a circle. Now, if you solve for cosine squared theta or sine squared theta, either one, you get this. So in this case, I did sine squared theta. Now the 1 minus cosine squared theta looks a lot like the form 1 minus c squared theta. So if we could plug it in, we could identically have the under the radical just sine squared theta. Then we can cancel stuff out, and it will look a lot cleaner, as you'll see in a minute. So proceeding forward, we let t equals cosine theta, which means dt over d theta, the derivative, equals negative sine theta. And then dt equals negative sine theta d theta. We plug our terms in. As you can see, this was the sine squared theta, became 1 minus cosine squared theta, and this was the dt, became negative sine theta d theta. So now substituting the identity in, we get the following. The radical and the square cancel, so we will have sine theta over sine theta, and then those cancel, so we essentially just have 1. So negative integral of d theta. Integrating this, we get negative theta plus c. And now what we can do is we can substitute back in for theta. Now if t equals cosine theta, then theta must be the inverse of that. So theta must equals cosine of negative t. And that is what we get by plugging in theta. So now that we solve the integral, we essentially solve the integral for both sides. So we can plug in this negative cosine inverse of t plus c for both sides, but just replacing t for x and y respectively. And we're gonna go ahead and clean this so we can do some more work. So here we are. Now, since this is an initial value problem, the next step would probably be to solve for c by plugging in x and y. Since now that we solved the integral, we're able to do that. So let's go ahead and plug in for y, and let's plug in for x. So next question is, how do we solve for these cosine inverse terms? Well, we bring out our triangle, and the reason we do that is because for cosine we go from an angle to a ratio, but now we're going from a ratio to an angle, so we're doing the inverse. So obviously you can see the angle, and then we're going to start out with focusing on the left inverse cosine. So inverse cosine radical 3 over 2, we're going to focus on following this cosine, so that's why you see the radical 3 over the 2, because this is what a cosine is, it's x over r, okay? Now, you can probably see that this is a 30, 60, 90 triangle. So if x is radical 3 and the hypotenuse, or r, is 2, then the y side should be 1, okay? But we're only concerned with theta here, which is 30 degrees, so we can just go ahead and plug that in. But in radians, what is 30 degrees? 30 degrees is pi over 6. So we go ahead and do that. We plug it in. And now next, we want to focus on the other inverse cosine. So we build a triangle for it. Obviously, we have the theta. Now here, the ratio is a little tricky, because we can see that it's 0. But the ratio is x over r, which means 0 equals x over r. But this, technically you can say this, how would this make sense? Well, we make sense out of it. Another way of thinking of it is like this. It's like saying that x tends to 0, okay? But if x tends to 0, let's picture how this looks like. We can imagine the triangle slowly, the x side getting smaller and smaller and smaller. Well, if the x side gets smaller and smaller, what happens to theta? We see that theta reaches pi over 2. So that is our angle, and we can plug it in. Solving for c, we get. So we can go ahead and plug back in for c and clean the slate. I'm going to go ahead and distribute the negatives, so it looks a lot cleaner, because too many negatives looks messy. Now, here we are pretty close to getting y by itself, so all we really have to do is take the cosine of both sides, and we pretty much have y by itself. Now, I'm going to go ahead and replace the cosine inverse of x termed with c of x for the next couple of steps, just so it looks cleaner. But once we're close to the solution, we will sub back in. Okay? So now this right here, cosine of c of x minus pi over 3, how can we break this up? How can we solve this? Well, this is a cosine difference property. And what that looks like is this, if you recall. So cosine a minus b equals cosine a times cosine b plus sine a plus times sine b. In this case, a is c of x, and b is pi over 3. So plugging those in, we have... Now, pi over 3 is 60 degrees. So bringing back our triangle, we have our 30-60 triangle. Now, essentially, we can solve for cosine pi over 3 and sine pi over 3 with the same triangle because it's the same angle. Now, if cosine... So we have pi over 3, which is 60 degrees. So the cosine of that is x over r. So this will become radical 3 over 2. But sine pi over 3 is y over r. So this will become 1/2. And we go ahead and plug those in. And now let's move everything over and clean the slate once again. And now we're in a position to plug the inverse cosine back in for c of x. Now, how do we solve for these terms, cosine of cosine inverse x and sine cosine inverse x? Well, this will just undo itself. It will become x. But how do we solve this? Now, the key here is to think of this. Remember, we said that if a cosine takes an angle to a ratio, but the inverse takes a ratio to an angle. So what we want to think of it is like, imagine this is a ratio, right? This is a ratio of a triangle, okay? But this will, solving for the inverse, will get the angle of that triangle based on that ratio, the x over r. But since we have this angle, what this was saying, now we're going to get the sine ratio, the other ratio, of that same triangle. Now, to see this in action, let's build our triangle. And obviously we have the theta. So like I said, this is going to equal theta. So cosine inverse of x equals theta. That means x will equal cosine theta. So we have this. And putting this into our triangle, it's like saying that we have x on the horizontal side and 1 for the hypotenuse or the r, because it's x over r. And obviously we have the y. So cosine theta equals x, so it's x over r. But here we want to solve for sine of theta, so y over r. So essentially what we want to get is y over 1. So what we want to do is actually solve for y. Now how do we do that? Well, we use the Pythagoras theorem, x squared plus y squared equals r squared. And the next thing we can do is obviously r equals 1, so we plug that in. And if we solve for y, essentially we get this, radical 1 minus x squared. So this is our y. Now, technically it's plus or minus, but since we're only concerned with the magnitude here and we're on the positive side, we just care for the positive. So sine theta equals radical 1 minus x squared. And then plugging that in, we have our solution. And that should do it.